If you can reach me on GitHub. If you want to get in touch with me afterwards, the old-fashioned way, I have some cards up here you can take as well. I'm going to talk a little bit about Riffyn software today, but but only for a smaller segment. I really want to put what Riffyn does into the context of the subject, which is the first time I'd ever heard a conference on this subject, and I thought it was really cool because usually you hear the word sustainability in the context of renewables and green and those types of subjects. But having heard the topic, it struck me that that's a really good point because so much of our world depends on software, and so little of it in many ways is built in a sustainable way. The two concepts are very, very intertwined. And so this talk is actually going to address both the concepts of scientific sustainability and software sustainability and how they fit together. So a little bit of background about what Riffyn is. Riffyn makes the Riffyn scientific development environment. If that sounds a little bit like an integrated development environment, that's on purpose. And the concept of Riffyn is to deliver lab data to machine learning in 30 seconds. And we can quite literally do that. Not for the biggest data sets, but for your average data set, you can. And by machine learning, I mean preparing all your data, annotating it, structuring it, getting it ready so that you can just put it right into whatever analytical pipeline or visualization system you want without the usual fuss with spreadsheets and data cleaning and chasing down people and going, what the heck is this about? And you forgot to annotate it, and what unit is that, and so forth. So the goal is to try to deliver more productive R&D across organizations. Our focus is industrial, and that's, partly it's because there isn't the money to support software in science, so we can't build a business off of it, so we give it away for free to nonprofit individuals. But even then, it's because the culture in science in academia is such that it's actually very difficult to succeed with a product that's about data integrity and longevity of data, because everybody's so short-term thinking in what they do in science. So we hope one day to have an impact there, but our focus is industry. We're based in Oakland, California. If you haven't visited, it's a really cool city right next to San Francisco. It's actually more interesting than San Francisco, but if you walk around, you'll see these giant murals all over the buildings that have been painted over the past 10 years. This is just one of them, Oakland A's baseball team. But they've got tons of these, and they're magnificent, 20-meter works of art that are just there for sponsored by the city. We support customers across the biopharmaceutical, biotech, chemical, food industries, and we also have increasingly focused on the tech transfer, the delivery of R&D, the products of R&D, which is essentially a formula or recipe to make a product, transferring that digitally to the manufacturing environment. As Nico mentioned, I started out in my career 25 years ago in biotech, focused on genetic systems and microbes, wiring up programmable logic using genes and proteins to get very predictable complex behaviors. That led to the genetic toggle switch, which led to, in some way, the field of synthetic biology. And then I turned towards statistical learning, trying to accelerate the understanding of cell mechanics using high-dimensional data sets, rapid acquisition of data, which necessarily invoke the need for computation. And I did that because after doing the work with switching the genetic circuits, it became clear to me that no matter how good we got at wiring a few genes together, we had no idea what was going on in the cell. And it was a bigger and more interesting problem to try to make that more efficient. But after some time in the statistical learning and microarrays, I became both inspired and frustrated at the same time. Inspired to actually put a product on the market, but also frustrated by what a mess scientific data was. So what I did, I was at Boston University at the time. I left my position there in the faculty, and I went to Amherst to try to help build the pathway that you can see on the right, which is the isoprenoid synthesis pathway in part, and central metabolism in part, in yeast. So we actually did build this pathway for producing farnesene, which is a 15-carbon small molecule that can be transformed into diesel fuel, makeup, oils, rubber tires, plastics, an incredible diverse array of products. And we did succeed in engineering yeast to deliver that molecule from sugarcane syrup with an efficiency that every academic expert in the world said was impossible. And the way that we did it is we actually pulled a pathway out of lactobacillus, and we put it into the yeast, and it bypassed that green arrow. About 2/3 of the carbon metabolism in yeast bypassed its native pathway and went through the pentose phosphate pathway directly into acetyl-CoA and then down into farnesene. And we got a theoretical bump in yield and an actual bump in yield of about 30 or 40%. So by the end of this project, those yeast were consuming sugar and sending 2/3 of it out to the secondary anabolic metabolite, which was ATP consuming, which is really crazy because ethanol, which is a typical fermentation byproduct, is produced at something like 90%. Best yields are around 93% weight for weight yields, but it's an energy producing pathway. It's beneficial to those organisms to make ethanol. Producing an isoprenoid is terrible. It doesn't like doing that, but we still were able to coax it into unprecedented yields. So that was a really fun project. But one of the chief lessons that I got out of that was how fundamental data was to our success in science and how bad we are at dealing with it, which was the same lesson I got out of my experiences at BU. So now academics, industry, same lesson. That led to me saying, I better do something about this. And that led to Riffyn. So what I'm going to talk about today is just this brief outline. Just a reminder of how fundamental software is to our world, our relationship with everyday life. How broken is the relationship that science has with that. How transformative it can be. Why we built the SDE, Riffyn Scientific Development Environment, and what that looks like. So I'll give you some videos of that. And then how that relates to sustainable software. So software runs the world. I saw this on the flight, and I just thought it was the coolest example. So I put it in here. This is the IBM floppy disk controller from 1983. And it was hardware-based. So the whole logic of controlling that floppy disk was embedded in the circuitry of these chips. Took a typical huge IBM engineering team many years to build it. 5 years before that, Steve Wozniak, I presumably know who that is, founder of Apple, built the same thing at the bottom by himself using software to engineer the logic. It was cheaper, more reliable, more flexible, stored more data, and it was simpler. And of course, much of the logic design that's done today is done through software. It was just an example of how fundamental software is to our existence today. Another example from a different industry, automobile manufacturing. In a sense, this is software. In a sense, this is even more fundamental. This is principles that are embedded in software. But this shows the gain in productivity over about a 20-year period, 15-year period, between the Japanese and the US automobile manufacturers. So US automobile manufacturers basically didn't improve at all. The Japanese did. Why? Was it because they had better equipment and tools? No, they were disadvantaged. It's because they applied the principles of quality systems, total quality methodologies, which were to make better products, but that led to dramatic improvements in productivity. Because in a nutshell, instead of making 2 cars and throwing one out because one didn't work, they'd make 1 car and it worked. While the US manufacturers were throwing every other car out, which is a lot of industrial capacity going to nothing. And you say, well, gosh, it's probably all the fancy automation and robots that did this, right? No, because look at the times. This was not during the time of significant industrial automation. This was using data and statistics and process engineering and lean to get this done. People engineering, behaviors patterns. That, in a sense, is software. And yet, when we talk about similar problems of quality in science today, most people immediately go, we need robots. No, we don't need robots. Robots will just make it they'll just make a mess at a faster rate than humans will if you don't do them right. So, this slide is stating the obvious, but it's sometimes useful. Basically, our whole existence is interpreting the physical world around us. We look at data, we interpret, we generate information, and take actions based on that. Actually, most of us usually skip the data part and just go straight to interpretation, but, which leads to a lot of arguments. But ultimately, that's what we're doing as people. And we have built these assistants for our lives, which in the form of software, that take the scut work and the drudgery out of a lot of that and do it automatically for us. So software, in a sense, is a personal assistant that is embedded in every part of our life. I don't have an assistant. I do all my travel reservations. Why? It sucks, but why do I do it? Because you go to Expedia and you type in where you're going to go and you make it. It's actually less work probably than going back and forth with an assistant and figuring out all the options. So software is basically becoming our personal assistant. And yet, despite that, we know that. We have computers in our pockets. We interact with it on a continuous basis. It's practically plugged into our brains. But in science, we still work like this for the most part, scratching things out on Post-it notes and typing them in sheets and putting it in spreadsheets. Oh, it's electronic. It's in a spreadsheet. Yeah, and how many people can interpret that spreadsheet? You can't. It's almost hopeless. So what people do is they look at that one scientist interprets the data in that spreadsheet for that one experiment, generates a plot, makes PowerPoint, and then tells everybody what the conclusion is, whether that's right or wrong. So software can help here. So I asked about 5 years ago, I interviewed 30 people across academics and industry and said, do you have these problems, kind of problems along the lines I just described? And most people said yes. And I said, what if you had a software application that could clean that up and it worked really well? What would you pay for that? And I got answers anywhere from $50 a year to $5,000 a year. But about half of the people I interviewed would pay less than $500 a year for software that would fundamentally transform their relationship with data. And I thought that was ridiculous, but particularly because at my lab at BU, we were spending $18,000 a year per person for reagents. And nobody batted an eye, not even a question mark on that. Of course you have to spend that on plastic and salt. And yet, software? Nah, I can get Microsoft Word for $100. Why would I spend any more than that? So our view of software is just fundamentally skewed. We value it for what it does for our lives, but we don't apply that to the economics of software. And I think partly it's because it's, number one, it's invisible. So it just doesn't seem like you don't have to make anything. The second is that we're skewed and biased by the subsidization of software that we get through Google, which is paid for with our advertising time. But it isn't cheap for them to provide that software. So why does this matter? Well, it matters for the reasons I was hinting at before. If you look at the amount of money that we spend each year globally on process-based R&D, life sciences, chemicals, energy, food, et cetera, not even the computing or physics or that R&D, just the process sciences, $400 billion a year. This is a few years old. I think it's been pretty flat for the past few years. And if you take most of the published studies on error rates in science, 50 to 80% error rates of false or partially false results, I take 25% being generous. That's still $100 billion a year of money that we're just throwing down the drain. Just like the auto industry was, throw every other car out. We're throwing basically half of, a quarter to half of that $400 billion a year down the drain. Another way to look at the same problem, the reliability of a $20 memory stick is 50,000 times higher than an average $500,000 research project based on the reproducibility rates. And people know this. I talked to one professor in Campinas, Brazil, and he said, I can't produce the output I want because I actually demand quality. And I spend so much time running around quality controlling all the crap that gets generated in my lab. I can only get a few things out every year. So we don't have to live this way, and data and software can be transformative, and I've experienced this. This is one of those, I think I showed this a few years ago, maybe Nico saw this. This is one of the stories. This is strain screening. I joined, this comes from Amyris. I joined Amyris in the beginning of 2008, and the team there was about 100 people already in place working to produce that farnesene molecule at a dramatically higher production levels. When I arrived, they had just seen this first jump in production from virtually nothing to now we're making this stuff. And then it was a few months of nothing, and then another jump, and everyone's excited. And then it flatlined for like 9 months, or maybe it was 7 months or something like that. And nothing, 100 people working on just make an improvement in one strain and nothing. That's scary for a startup that depends their entire existence on success. Then we started to look at other ways to do things, introduced 96-well plates, took the measurement of these strains out of the hands of individual scientists and centralized it into a core. Did not use robots, did not use any automation, just put it into a process. We reduced the error 6-fold, and I think within 2 weeks of doing that, we found our first hit after nothing for all this time. Was it because of something magical about plates? No, it's because we took the error down to a level that we could actually see real signal above the noise. And guess what? We kept seeing hit after hit after hit, and they were real. Because most of the improvements you see aren't these giant leaps of 2x that we've come to believe are expected in any biological experiment. They were 10%, 15%, small improvements, but they were real, and you could just keep stacking them. Those come fast, and if you added it all up, it doubled our rate of progress. It probably saved us from plateau and death, but if you just assume that the previous rate would have continued, it was a doubling of the speed of our research with no additional increase in staff from quality. So that was the first, eye-opener for me. And when you look at how we found some of the improvements that went into this, this was later on, so this is kind of an anachronism, but after we've been running and we were starting to automate some of these screening programs, tracking a lot of data, this was an example of the kind of error that creeps into your processes you don't normally know about. What you're seeing here is each column of points is a different 96-well plate. All the measurements from that plate, the red is controls, and you're trying to find strains that were improved above the red statistically significantly. Every 5th plate was dropping. Somebody noticed this in the data record. And they thought, well, we could have just ignored it. Who cares? It's every 5th plate. Well, maybe that's the winner is in that plate. It's also a waste of resources. So they wanted to fix it, and they dug in and they traced those every 5th plates to a specific spot in a specific height of the deck of the shaker incubators. And when they looked at that, they noticed the plastic gaskets were worn down from all the shaking. And they had the hypothesis that might have something to do with it. They took out those plastic gaskets and replaced them with stainless steel so they couldn't wear down. Problem went away. So basically, the theory, I don't know if we ever figured out root cause, but I would theorize that it was an aeration problem. You weren't getting good aeration and shaking of those plates, so they weren't growing. Those kinds of errors add up, and they make a big difference. Another example of this, and these were just, I have like 100 of these. I'm not going to share them all, but this is the other one I'm going to share is is in a different realm of science. It was the scientific, the product life cycle. It was scale up from fermentation, 1/2 and 2 liter scale to 200,000 liter aerobic bioreactors. And that's the farnesene product that's coming off the line that gets purified into the clear substance on the right. Just for relative scale, the compressors that drove the air through each one of those was about the size of, I think, about 3 semi-trucks. So massive compressors bubbling that up. And a person would be, I think these are 8 stories tall, these fermenters. So really big stuff. So to get you don't want to do experiments in that scale. It's really expensive. And yet, as a startup, they did. But to get your science from that microtiter plate to that large scale, you have to integrate a lot of stuff, a lot of scientific disciplines, a lot of equipment, a lot of data, from screening to bioprocess development, recovery processes, analytical chemistry, regulatory and safety testing, and then scale up piloting and so forth. Our first attempts at this were terrible. It would take a year to get things across. It would always drop double-digit percentages in performance. Everybody pull their hair out. We'd rip the fermentation scientists out of their seats in California, send them to Brazil. They go there for 3 months. Their research was just totally disruptive, but you had to get it to scale, and it was just a mess all the time. And when you lose that kind of percentage performance, you're losing hundreds of thousands of dollars per batch, because those are big fermenters. It's a lot of money to throw down the drains. This was not fun. Well, we fixed it, and we were able to go eventually in 3 months' time from a half-liter reactor to a full-scale 200,000-liter reactor with exact performance matching, with nothing in between, no intermediate testing. And the reason ultimately we could do that was harnessing data. So one of the many reasons that led to that kind of improvement in performance was the ability to actually see what was going on in fermentations. On the left is the fermentation data before we got serious about quality. On the right was the same fermentations after quality improvements. So what you see on the left is just kind of an average performance with lots of noise around it. What you see on the right is an amazing amount of physiological and physical structure that's going on. Each one of those kinks and turns and dips, there was a physiological reason and a physical reason for every single one of them. And they led us to the root causes that allowed us to not only improve our strains, but stabilize the process so that when we got a number, it wasn't a false number, it was real. And what it also did, and this is probably the most amazing part, is we ran hundreds of experiments, hundreds of fermentations, not all for different kinds of reasons. But if you looked at just one of those weeks' experiments, that's what you'd see. You'd see this tiny little window of data around the relationship between certain parameters. When you aggregated hundreds, suddenly these relationships started to come out. This particular relationship, we didn't have, I think, a single experiment in the entire set that was done to test this relationship. It's just that the natural variation in experimental conditions, which we were tracking, was actually doing an aggregate experiment. And because the quality of those experiments was high, we could stack all those data in an absolute way so that it was one giant experimental record. And that led to a relationship which explained the physiology, which we put into a differential equation model of the fermenter and physiology. It was a very complex 3-equation metabolic model, but it predicted, that simple model predicted that if you add more water to the beginning of a fermentation, you get 5 or 10% more product out. And it worked. So a cost-free improvement all derived from a relationship which came from aggregate data, which came from quality in the first place. You cannot do that in your average scientific environment in academics today because nobody cares about the experiment beyond this week or maybe this month. And that's where I hope as a society we can get to. But it'll start with industry and hopefully it'll propagate to academia. But either way, you can't do this with just notebooks and spreadsheets. You have to do this with really good software and really good data practices. And even more importantly, you need to do this with an understanding of data principles so you can design the right experiments. Yet this is how we do it. This was an actual diagram sent by somebody from the manufacturing plant to R&D saying, this is how we're doing it. I don't understand why we're not getting the same result you are. I'm like, I wonder what kind of cars we'd be driving if that's how we did automobile manufacturing. But why do we do that? Because the designs of our processes change so quickly that you set up a software system or a database to deal with it, it's obsolete as soon as you finish it. You've already moved on to the next experiment, the next process. It doesn't, your database is just, it doesn't keep up. It's constantly happening. So we had great data systems at Amyris that helped us to draw those conclusions. And at the same time, we had people right next to the right next to the people using the databases, they were using Excel and paper and all kinds of crap because they didn't have an adaptation of that database for their need. This is when I said, okay, it's time. I got to go do something about this. And this is what led to Riffyn. And this is the actual song from my son's guitar manual that led to the Riffyn's name, which has nothing a priori to do with what we do, but it was 6 letters or less, and there was 2 hits in Google when I searched for it. So that was the name. Post hoc, it's actually a great name because the whole concept of Riffyn is to riff off the last idea like a song and build incrementally on it and build a data system that could support that. The why is because I needed the domain name. And then I saw this thing at the top. I said, that works too. I saw this after I took a picture like 3 years later. I hadn't noticed it, but now I'm found, was blind, now I see. And that's actually what we're trying to do, help you to see your data for the first time. So 2013, I wrote down this business hypothesis. Businesses are driven by processes. We may not realize it, but everything we do is a process in our workplace. And our advantage as a company lies in the optimization, improvement, re-engineering of these processes. But they're usually inefficient and unoptimized because they're invisible. They're invisible because the design and the data systems, the design systems for the processes and the data systems to track them can't keep pace with rapid iterations. And so we just don't capture them. So we end up with napkin sketches of our process. So Riffyn scientific development environment was designed from the beginning to try to capture our data in a context that allowed us to continuously innovate. But to do that, you can't capture the data disembodied from the process that generated it because you can't understand it, first of all. Second of all, you make a change to the process. Well, what are you changing? There's no record of that. So you have to go for broke. You have to go for the whole pie, really, if you want to solve this problem, from experimental and process design to data capture and execution of experiments, data integration to analysis. And that's what, unlike traditional data systems which just focus on capturing data, we're going for everything. And it's been a pain in the ass, I'll tell you that. It's a lot harder than I anticipated because you're changing minds, you're changing hearts. You're teaching software engineers science. You're teaching scientists software engineering, and all of these things are much harder than it would seem. But if you do this right, you get a full loop of iterative improvement, not of your product or your scientific result, but of the process by which you generate that, which is the important thing at the end of the day. Because it doesn't matter what you say you found, if you can't prove it, it's actually not terribly valuable. So what that looks like in Riffyn is, first of all, a visual process designer. Upper left is kind of like a Visio diagram. You can drag and drop the steps of your experimental process. This is not a computational workflow. It doesn't compute data from step to step. It is documenting the physical transformations in your lab, inputs on the left, outputs on the right. Same paradigm as a compute workflow, but it's actual physical stuff that it's tracking. Data and samples are tracked here. Procedural information, pictures, video, and some unstructured observations and text over on the right. You can execute these processes and suck data in from all the myriad of data systems, whether it's files or databases or whatnot. You can attach the analytical scripts you write to analyze the data are attached right to the version controlled process so that, and then it's locked so that if you want to look at what was done later, you simply download the data, and I'll show you this in a second, and you download the script that was used on it, and boom, you can reproduce the result. And then to make all this useful, first of all, it's not useful no matter how pretty your interface is if it just gets stuck and isolated in a walled garden. You got to get it out. So Riffyn takes all of that. It uses the graph of your experimental steps in it and all the annotations in it, automatically reshapes and structures your data into a statistical data frame that's stacked, experiment on experiment, process version on process version, all the way up to present day. And it leaves gaps if there's misalignment, like you deleted a variable or you added a variable, but otherwise it's all integrated. And then you can feed that into any third-party analytical tool in seconds. And we made this decision very intentionally. We were not going to try to rebuild the brilliant analytics that were developed externally, because it's a waste of time. We'd never do as good a job with it, first of all. And it already exists, and those tools are great. So let's just get the data there. This has been the hardest thing for me to explain in trying to raise money for this company. They're like, where's the plot? Where's the analytics? Where's your machine learning? It's like, that doesn't matter. That's the easy part. It's cleaning the data and getting it there that's the hard part. We put machine learning in the tagline. That was our, we said lab data to machine learning. See, now we have machine learning. By the way, this sounds ridiculous, but that was enough. That's what did it. Now we got investment. So yeah, anyway, I'm trying to prevent myself from getting distracted on that. So this is what it looks like. This is a video. I have a couple of 1.5, 2-minute videos. This is an interface for, basically it's like your Google Drive of processes. And you open up one of those, anything from HPLC processes to pharmacokinetic studies. You can create your process on the fly, more or less. You can pull from controlled vocabularies the inputs and outputs of each step. There's a cell culture you're adding as an output for that batch fermentation. And you can do the same thing on the inputs. You want to get a bioreactor, you want to get a media. It's all coming from controlled vocabularies. You can annotate this with with properties that have units associated with them that are relevant to that property. So you can quickly create a structured definition of the process or experimental flow that you're doing. And usually you don't have to recreate these from scratch each time, because what you do in the lab, you do over and over again with slight variations. So then you can extend this, take samples, you can split and branch, because obviously when you take samples, you send them to multiple different analytical procedures, or you might mix things so you can merge things together as well. And then you can annotate it with the procedural information. Okay, what do I do in each of those steps? And then you can take those annotations and augment them with pictures and video to help explain how to get things done. And it's not a very interesting video, but that's all embedded into this. The whole thing, you can see, you might have noticed, it's all version controlled like source code. It's not as powerful as GitHub yet, but we're evolving the product to the point where you'll be able to diff these processes, branch them, independently develop them, do another diff, merge them together, branch off this way. So your actual experimental procedure becomes the source code for science. That's where the concept of SDE came from in some sense. So once you've built this process, collected data, I'm skipping the data collection part in the interest of time. You can add, there were 3 experiments on this process. The experiments are collated on the process. You can export all of the data. You can get it through a REST interface, or you can pull it through the UI. And we'll have a ODBC, JDBC query interface in a couple of months. You pull it, it computes it across the graph, compiles it into a CSV. Yeah, it's pretty low tech, but that's on purpose, because anything can read a CSV. And I open it in Jump. It's my favorite analytical software. Not free, but really powerful. And I also downloaded the script that was embedded. I'll pause there, actually. You'll notice the script to analyze this process was just embedded as a procedural item, version controlled and locked with the process. So I downloaded it, and you can upload a different script if the process changes and version it. And then I opened it and ran it against the CSV file that was also downloaded, and then clicked the different analyses. And this is a time series plot, which is all interactive. You can select different strains. This is strains run in 3 different experiments that are being compared here. You can run root cause analysis, doing multivariate regressions of upstream variables and how they impact the measurements in the HPLC, which were downstream of the fermentation. And you didn't have to copy paste anything. You can see the annotations, the unstructured annotations over on the right, and how they're linked to the time points in the process where they were actually taken. And then you can mark particular time points with and say, hey, I want to follow up on this. This is marking it in Jump, but we actually have an add-in that allows you to write those markings back to the original data in the system so that future people can see the markings. You can run a process analysis, generate your control charts, look at where things are falling in or out of spec. You can select those points and then see where those points land in your fermentation profile. So all this data is all linked together, completely interactive. You could run it through pre-programmed analytical pipelines that do automated analysis, or you can drill down into it yourself using tools like JUMP. So some of what I showed you is actually the power of JUMP. A lot of it is the cleaning and presentation of the data to JUMP, which is done by Riffyn. You need both. And we developed a system with an ecosystem in mind. You can't do everything, but do what you do really well and make use of other tools. One of the most profound realizations of the past 5 years of doing this software engineering effort, there's two. One was how hard it is to get people to do something different. I knew that was going to be a risk. I wrote it down on day one, but I underestimated the difficulty by an order of magnitude. It's 10 times harder than I thought it would be. The second is how hard it is to communicate science to software engineers, and how much time we've lost making mistakes on what we build because they just didn't understand the problem they were trying to engineer, so they couldn't make all those micro decisions in their work the right way. And I'll come back to that. But on the subject of people and change, software is designed to deal with data about your world. So we get tired of dealing with it manually, we build software. That gives us transparency and automation, better use of data. And if software is worth anything, the whole point is to change how we interact with the world. So the whole point of software is to change behaviors, which leads to new, more different data, which changes the software, and the cycle repeats. And if software is not creating change, it's a waste of time. So this is the purpose of it. And yet that means the software is not a static object. It's a living organism that's evolving with our evolving behaviors. So good software drives behavioral change. That's lesson number one from my experiences. It means it needs to evolve because behaviors will change continuously. And surprise, surprise, software doesn't evolve itself. Maybe it will one day, but it doesn't now. So besides making software that can adapt itself, in a sense, Riffyn's trying to make software that can constantly change just by drawing a new process and adapting to that process. That's not enough because the way people interact with it has to change too, and that means programming the software. So this is a simplified map of Riffyn's software development lifecycle. And I will bet that very few people in academics do this. And I will tell you that even though we have about 22 people on this project right now, we are still half as many people as we need, and we are not doing a good job of living the software development cycle because it's very, very intensive. So I'm going to illustrate this rather than explain this graph, but the big picture features are everything from defining the need, defining the problem in a generalizable way, feature development, breaking down the work, tracking the work, quality testing, customer user acceptance testing, documentation, help docs, release scheduling, bug fixing, and on and on. And that's not even the whole thing, and I'll come back to that. So step one, what are we going to build? Building a roadmap that's based on an understanding of what the customer needs, what you can build, what your business needs are, and what your priorities are. That's an effort unto itself. Step two, once you decide to build a feature, you have to design it. You don't just start programming it. So specifying the specs or requirements for the feature, designing the wireframes, building the comps. And I want to show you how intensive this is. So one of the features we're building right now is just a stupid, simple modal that is going to allow you to search for samples or equipment or any other object based on temperature, time of use, any property of that object you want. Get a list of them, and then save them to your experiment to use in that experiment. This is the design specification. As you can see, don't comment, it's not done yet. This is what that looks like. Okay, 20 pages later. That's just for one modal, and that's all it really does. It does a few other things, but not that much more. And then that still needs to go into the design specification and then go through iteration. Then we'll program it, won't work right, and then we have to debug it before we release it. And then we have to do some design changes, then we'll release it. And then there'll be problems there, and so on and so forth. So that's just design. So now we've decided to build this thing. We know what we're building. The developers have to look at it. They have to estimate what they're going to do and how much effort that's going to take. And they have to write these tickets in Jira. We use Jira. There's other systems to do this. But a set of tickets where there are all the sort of project elements to get that done. Then we track their progress against those elements. So each one of these curves is a release. It's all the reasons they go up is the creation of all those work tasks in order to get the release done, and then the burn down of those tasks as they get ticked off. And you can see some of these start getting planned months, almost a year in advance of building, and then they crescendo into like full scope, and then they get burned down, and they sort of go through this cliff typically as people knock things off. But we need to track that because we need to deliver on some reasonable time frame. Then after that, after we work all the bugs out in development, which often takes weeks after code release, and all the code, by the way, is peer reviewed, and it's also goes through static code scanners for security gaps and everything else, automated builds, et cetera, et cetera. After all of that, it goes through final QA, and if it passes, we generate an IQ and OQ, installation qualification and operational qualification test, which is a combination of manual and automated tests because the software has to work in a GXP compliant environment. So we have to do those tests, have the test plan and the results, save those in an immutable record so that if we ever get audited because our customers got audited, we can point back to this particular release was actually tested and worth working. Then you have to write the release notes and the help documentation, and you post those. Then you have to communicate with your customers and schedule, because this is enterprise software, you can't just pop it in on them and blow up their work. They want to have a rollout plan staged and carefully staged. So, and that, by the way, is just the release. We typically get, unfortunately, and we want to make this better, but we typically get a few dozen to 50 post-release bugs, and they're immediately triaged. Are they critical? It's blocking work. Drop everything. Blow up anything you were doing and fix them. Or is it highest to get it done as fast as possible, but don't lose sleep over it. High, get it scheduled, et cetera. So those are very disruptive, but it's inevitable in software. And that's just the software development. If you want to sell this product to a Novo Nordisk, you have to have data redundancy. So we have 5x data redundancy, 3x real-time failover. So there's 3 copies of everything in every service running at the same time in case one goes down. There's 2 more to back it up, and that'll happen within 10 seconds. And then 2 more copies, one of which is saved 3,000 miles away, static snapshots every 6 hours for 395 days. Latency compensation, physical security barriers, restricted access, end-to-end encryption. We have to be compliant with OWASP top 10 security principles. We get external penetration testing to try to hack into our system on purpose to see what our weaknesses are. We are ISO 27001 compliant, 21 CFR and Annex 11 compliant. Our systems are now OS hardened. They're actually immutable. So we actually put the whole image for every service on a Docker container. It is immutable. So no, you can't hack into it. And all of that's behind a firewall that you can't even get into in the first place. So that's just to meet the security concerns of our customers. And then there's help. So help desk, 24/7 urgent support, issue resolution coordination. If you get a critical bug, everybody's going everywhere. There's got to be somebody that's on following that and communicating with the customer. So that's the project management side. We have to guarantee uptime, maintenance, upgrades, response times. Then there's legal, confidentiality, data protection. We have audits. We've been audited by Novozymes 3 times. Their head of security has actually flown out to California for that? And then what if we blow up as a company? Or we just stop offering the product? Code escrow, operational escrow, what are we going to do about that? Disaster recovery. What if Amazon, which is where we run our stuff, their data center floods? We can get the system back up from scratch. Our target response is 48 hours. So take the static snapshot, rebuild the entire system from scratch, and deploy it and back to the customer in less than 48 hours. And then there's getting people to understand how to use it. We have a whole scientific consulting team that's job is to go to the site and help teach people how to use it and set up their software. So that's just for one part. You saw the product, right? It's like, Visio, drag and drop and, compute some data. All that just for that simple, stupid product, right? Yeah, it's crazy. And then there's the bugs that I mentioned before. Right now, I'd say 50% of our engineering effort, and this kills me, it's truly killing me, is going towards maintenance and bug fixing. I would like that number to be like 20%, and we're trying to get better. But at least I know that our pharmaceutical customers are worse. They're spending 70% of their IT on maintenance. So that's not good, but, and we're going to try to get better. But that's the reality. So to conclude, science has had a profound impact on our lives, obviously. Everything has been touched by it. But it's kind of a mess right now because it hasn't introspected. It hasn't evolved with the times. And if we want sustainable science, science that can not throw billions of dollars to waste and deliver the improvements in our quality of life we need as a planet, we also need to back that with sustainable software because it isn't getting done with pencil and paper. And I'll finish with this final story. It's very relevant because it's Scandinavia. Have you all visited the Vasa museum? Wow, I love this museum. Went there like 15 years ago, and it's stuck with me forever. You probably know the story better than I do, but I'll say it anyway. So, King of Sweden didn't like the Poles. He wanted to show them who was boss. So he's like, I'm going to build a ship. It's going to be bigger and better and badder than your ships. So he took the standard ship and he added another deck to it because it was going to be really tall and really imposing and threatening. So they launched it off. They just added the deck, launched it off, put all the dignitaries on it, went out 200 meters and blew over and then sank to the bottom. Because they didn't engineer this thing. They didn't design it. They didn't actually use any principles. They just said, rule of thumb, well, let's put another deck on. That was 400 years ago. We don't build ships that way anymore, obviously. We're a lot more thoughtful. But science, Newton, and the scientific method emerged around the same time, pencil and paper observations. Guess what? We're still pretty much doing science the same way we did 400 years ago. And that's not acceptable. And that's part of the problem. We need to change. We need to bring in blueprints and computer-aided design and design of experiments and statistical methods and all of that, data science. That needs to be part of our lives as scientists, just the way that it's a part of an architect's life or a software engineer's life or a mechanical engineer's life. And we're not yet. And I have various theories why, but that needs to change if we want sustainable science and sustainable software. So, thank you.